we have Professor Euclides Mesquita from the School of Mechanical Engineering. He's going to talk about the dynamic response of rigid structures and plates embedded in transversely isotropic layered media. And before that, he will spend 10 minutes to give a presentation, an overview about our university, which is important and very nice so that people can have a feeling of what the University of Campinas is. All right. Thank you, Euclides, very much.
Thank you, Munir. So, good morning to everyone. So I figured that we have guests coming from all over, and they're going to stay very little here, and they spend long trips. So I talked to Munir, and we decided to make a short presentation before my technical talk about the University of Campinas itself, so that you can have an overview of where we are, what we've been doing the last years. So after that, we go to the technical talk. I'll speed up a little bit, but I hope it works. So the University of Campinas UNICAMP is a public state university. We have in the Brazilian higher education systems, an overview of the Brazilian higher education systems, we have 6.5 already million students enrolled, which is something like 14 to 15% of the cohort between 18 and 24 years. This public system comprised of 58, now it's something like 62 federal universities. There are state universities as well. And in the São Paulo state, we have 3 state-funded universities. The University of São Paulo, which is the largest university in Brazil, the University of Campinas, which is the university here, and the University of the State of São Paulo, which is spread throughout the whole state with 23 campuses. And that's very confusing, the name, but it is so. It's spread through the campus. From this 6.5 million people enrolled in higher education, 70% of them are enrolled in private schools, and most of them are for-profit schools. So only 25% of the students are enrolled in this public system that I have briefly described here. Who are we? Well, we are seated in the city of Campinas. There's 1.2 million people. We are producing this area here. We have we produce about 8% of Brazilians' GDP, and 3% of the whole. Yes.
The 14% including the private schools.
Yes. This is 14% private and higher education. So
that's very low.
This is a low issue. We know we have a problem to tackle there. We are aware of this. And of this, only 25% are in the public system. It's in the public system. So Campinas is a relatively well developed there, with 3% of Brazilian GDP being produced around it. We have the UNICAMP here, and around Campinas we have almost a high-tech pole. We have a synchrotron light lab. We have another Catholic university here. We have Samsung and CTI, which is a informatics and technology center. We have a research institute. We have another faculty. So there are groups there's pharma concern and research here. There are other communications companies. So around this area here, we have a sort of a technological pole. Well, where do we live from? What do we live from? This is our budget from 2010. We live from, state pays us 2.2% of their next sales tax. This amounts to something like $1 billion a year. That's the money we mainly live from. Unfortunately, we spend a large part of it in salaries. We also get something like 3.50 million from other sources, mainly from research programs. In all the Brazilian system, the public Brazilian system, there is no tuition fees at all. All public universities in Brazil are free. So there's no money coming from tuitions or fees. The university itself was founded in 1966. We have now 24 schools and institutes. We have 3 hospitals. We take care of 3 hospitals with more than 800 beds. We now have presently about 1,900 faculty. And all, you don't know if in Brazil there's research universities and teaching universities, and the teaching universities you're not necessarily required to have a PhD to be faculty, but it's not the case with us here. We have, except for 6 or 7 or 12 people there from old times, we have all PhD is a requirement. We also have a large staff, about 8,000 people working at the university, half of which is working in the hospital area. Health area is
all these staff considered as public service officers?
They, well, from 89 to now, we changed, we are all were public servants at the beginning. By 2-3 years ago, we had 50% public and 50% private, but we are going back to the public, this administration is moving back to the public servant model again. So this is an ongoing issue here. So if you take a look at the students, the figures haven't changed much in the last years, but we have about 31 to 32,000 students. Just about half of it are undergrad, the other half are graduate students. We have about 11,000 degree-seeking graduate students and about 4,000 non-degree seeking students that are here for specializations.
In Master of Science, do they have to write a thesis?
Yes, they all have to write a thesis. It's a 2.5 year programs with courses and then a thesis to be, and you have to have an oral examination at the end with a committee and so on. So this is very formal, still the old way. What we are relatively proud of is that we have very good students, and the reason for our good undergraduate students is here. We have something, we do our own entrance examination every year. And we have something like 6,000 applicants, and we offer 3.5 positions. So we have something like 18 to 1 candidates per position here. So this is usually the students that come in are very good students.
So in this case, because your university hope is entry examination, so if they fail to get admitted by your university, the student has to take another examination.
Another examination. Sometimes, presently, you have to take, if you go to the 3 state universities, you have to make one entrance examination for each state university, plus the federal. The federal system is trying to create a joint national examination. It's been implemented, it's partially implemented, but will grow, and sometime when it's mature, we probably will join, I imagine that university will join. It makes more sense to have a national like Abitur in Germany than every university. This is a very issue because in order to have students from all over the country, we used to make these examinations in 17 different cities, so we can attract people from all over, not only from São Paulo. But this is also an ongoing debate. But in medical school, we have 115 to 1. The rate from applicants to places. This is very high. Engineering is 30, 25 to 40 according to engineering. Civil engineering was going down some years ago. Now in the last 6-7 years went up to 40 to 1 again. So this is according to the market.
And even for the student that study in the medical school, they don't have to pay any tuition?
They don't pay anything.
That's good.
That's good, right? They really don't pay anything.
For those who get in, it's very good.
Very good.
Yes. It's hard to get in. So there's something interesting in Brazil. The Ministry of Education has an agency called CAPES, and they do an assessment of all graduate programs in Brazil. There are 4,500 graduate programs in Brazil, and they all are evaluated, assessed every 3 years, and they are ranked. So you can get from be graded from 1 to 7, and you can see this is the lowest, this is the highest. You can see the most of our graduate programs are from 5. This is very good, excellent national programs. 6 and 7, there are requirements that they have a decent degree, a high degree of internationalization with faculty exchange, students exchange, and so on. So we have 40%, 50% of our programs are 6 and 7. If you add the 5 We have something like 82% of the programs.
Oh, this is the higher the better, right?
Yes, yes. So, yes, as we go to more 7, we improve the quality of the programs. This is the national average. So we see we are much higher than the national average. Actually, when you do a arithmetic, non-weighted, and evaluate these grades arithmetically, we have the highest grade in Brazil. The graduate programs have the highest average in Brazil, over 5.4s. So only to have a view that we have a very interesting graduate programs. So we have graduate programs with grade 7 and 6. You can see most of the ones that are represented here have grade 7. This is engineering, this physics, this chemistry. So what we, and some biomedical as well. So actually the CEPID is constituted of people coming from grade 7 graduate programs here. So this is what I wanted to show you. We are strong and weak. This is one of our weaknesses. We have very little number of foreign graduate students. It's by 4 or 5% of the total numbers now. We did an effort to increase these. We have increased, but they come mainly from South America. And you can count the ones that come from Germany. So it's really small. So this is something to be improved significantly in the future. We are aware of it. So we've been granting master and PhD titles, and so we've been granting something like 1,200 Master of Science awarding these titles per year, and we are awarding something like 800. It has increased by almost 900 from 2010 to 2015. So we are awarding about 800 to 900 PhDs a year.
So what are the PhD students graduate to? Do they become academic?
In Brazil, still most of the PhD students go to the academy. In engineering, there are now some industries who are absorbing the PhD students, but only in a restricted amount. In Petrobras, Embraer, some pharma and chemical industries, but most of them are still going to academia.
So they will graduate here, will go to another university to become a professor.
Yes, that's the.
You don't take your own graduate to become a faculty member.
It's possible. We have a national context here when you hire faculty. It's a context, and actually you cannot forbid any graduate from here to enroll in this context. So there's a public. It's a public context, and you cannot exclude anyone. So in principle, if the guy that graduated here is better than the others that are applying, he'll get the position.
Okay.
So there's no barrier in this sense, other than the quality of the.
And quite often that happens, the hypercritics.
We used to like the excuse, use the excuse that if we produce the better students, we always get the faculty, the guys that are getting in ours. But there's also an effort to bring people from abroad and enlarge the number of candidates, and this is important to renew the university. We are aware of this, but right, Professor Valmont. So this is also a measure of what we've been. We don't only graduating. We have increased the number of scientific publications. For instance, in the Web of Science, by '89 we had 350. By now we have something like 3,000 index articles per year being issued.
This is publication, not citation. Right?
Yeah, this publication, just the publications. So I think with that, and the publications make frequently cover of prestigious journals. So to say that's not only number, there's quality as well. We have I'm finishing. We have an innovation agency. We're the first innovation agency founded in a Brazilian university in Latin America. And we deal with intellectual property, technology transfer, and we also offer an incubator. Just for you to have an overview of where we are, what we've been doing. Okay, thank you for that. So I think we should move to the next presentation. Okay, now the technical part. The title is Dynamic Response of Rigid Structures and Plates Embedded in Transversal Isotropic Layered Media. But I will address this issue, but I also like to give an overview of what our group has been doing in the last years. This is a collaboration with Professor Nimal Rajapaksa, who's a long experience in solid structure interaction, and also Josué Labaki, we co-supervised him, and now he is a postdoc at Simon Fraser with Professor Nimal. So the outline, I will talk something about the motivation. You will see that this is related to building a new synchrotron light source in the vicinity here, about what we have done to model the foundations of the synchrotron light source. We'll talk about soil profiles, plates, which is the kernel of this presentation. And I will then talk about the Green's functions, the exact stiffness methods for layered media, how we model the rigid plate, and how we model elastic plates. And we'll make some remarks on the future developments we are going to take. So very close to here, we have a synchrotron light source laboratory, about 800 meters from here. It's a small lab, and Brazil is now in the process of building a large, this is the present synchrotron light lab. And we are in the process of building a larger synchrotron lab. This is the present one. It's a much larger one. It's the 4th generation one. And this poses some challenges regarding especially vibration requirements of the structure itself. If you take a look at the National Institutes for Standards, they have issued two requirements, or two quotes, vibration criteria for nanotechnology facilities. It's been applied in the US for nanotechnology facilities. Two of them are complementary. NIST A, for instance, requires 0.25 micrometers displacement, maximum displacement for frequency to 1 to 20, from 1 to 20 hertz, and 3 micrometers from 20 to 100 hertz. NIST I1 is another criteria, given in terms of speed, also for different frequencies. I wanted to show this because this is very strict vibration requirement. So this is a nanoscale, actually, almost touching the nanoscale. And two things come from this. The way the people are building labs, the synchrotron labs, I understand, they are to some extent trial and error issues. You can model, but you cannot model with 10-9 digital significant digits. You cannot measure properties, so there is a cooking recipe to build a synchrotron lab. But to the idea, and they did a lot of measurements here and data as to find out the foundation models and which way they're going to use, and are building, it's being built actually now. But we tried in the past to model a nano facility, a microscope facility, an electron microscope facility. There was already built, so we build a model and take measurements, and now we have a relatively good understanding of the dynamics of the electronic microscopes there, what's going on there. The idea here is just about the same, to have a model and develop and calibrate it later on, that we know if something is happening, what's probably the cause. Is external vibration, internal vibration, we should have more power. We'll discuss a bit about this. So a typical synchrotron light source that's working well is in the Diamond synchrotron in the United Kingdom. You can see here it's actually a forest of piles, and you put a concrete slab on it later on. I know that we talked to people. Spanish did not use the pile foundation; they used only a raft there, and they have problems because it's not that it will not work. the issue is, if it vibrates, you don't get the necessary focus on the beam. So it will work, but if you really have a stable foundation, you have a more efficient system by having better focus on the light beam. So when we started doing this, we decided this project that we would like to simulate. There are 3 parts in this. So one part is determination of soil profile. They did a nice job on this. There's the basic modeling of the system. We have plates to model, piles, plate piles, coupling, pile groups, and also wave propagation from inside and incoming and outgoing. And there are some also engineering and design issues which are related to mass distribution of piles and so on, which we'll not address. So from soil profile, we did a model, we modeled the microscope foundations. We did some, we took data from a colleague that worked here. So we have a really up to this is depth. Again, this is shear wave of the soil. So we're almost constant shear wave velocity through the depth here. So we are using, we know something about the surrounding soil. It could be modeled in some areas as half spaces.
Basically soil or it's rock?
It's clay, basically. So the issue, when it comes to now to the issue of modeling, we would like to, there's some issues about what we're going to try to model a flexible foundation resting on a group of piles. A lot of work has been done on this. A lot of work has already been done on this. But there's some challenges to be able to model this with a huge number of piles, up to 500 piles. And we're starting with the model, axisymmetric model, as we will see. As we move on, we might have to, the improvement will have to go to 3D analysis, but this will be work to be done in the future. So I'd like to say something what we have done so far on the dynamics of the plates. We are working on piles presently and then on the coupling of piles. I hope to be able to present something about piles next year. So we have rigid plates, elastic plates, and the surrounding soil. For rigid plates, we use a very classic, well, I also want to say that the linear here is stationary, the frequency domain, and linear, because the displacement and we had over there as a vibration criteria are very small. So everything is within the linear range here, and I think it's acceptable for that vibration requirement there. So we have an approach to discretize the interface, soil foundation interface or place interface. We can deal with horizontal and rocking loading. We can deal with vertical loading, and we're also focusing on the coupling, rocking, and horizontal degrees of freedom. As we come to the elastic plates, we will have a variational formulation, a constraint energy functional. We'll be dealing mainly with vertical loading. The surrounding soil models we are addressing is the transverse isotropic continuum. We have homogeneous half space, full space. Loads can be buried within the half space or full space. We may address a bimaterial interface, and especially we address the rocking and horizontal rocking degrees of freedom coupling. And we also have actually layered medium. As we'll see, horizontally layered medium. So this is the catalog of the problems we wanted to address at the beginning, and we've been developing solutions for this throughout the years. I think we have solved all of the cases that are here now. We can, from the homogeneous soils, we have full space, 2 full spaces, buried load, and half spaces. We have bimaterial interface as well, layered media with loads or structure placed anywhere in the media. We have horizontal degrees of freedom, we have a rocking degrees of freedom for all these cases as well, and a coupling of them. When we go to the elastic plates, we've also did the elastic massless and with mass. We've added inertia to the plates in the last year, so we have results. We are able to deal with all these problems here. How do we model it? The key issue, I'm looking at that. The key issue is to find the Green's functions regarding the solid. The solution is to find Green's functions for transversal isotropic media. There's a solution proposed by one of our students, Professor Mao, some 20 years ago, which was based for transversal isotrope. It's based on the Hankel transform, use cylindrical coordinates. You may use axiomatic or non-axiomatic solution. And the idea is to have an expansion in Fourier series in the axisymmetric in the radial direction for the non-axisymmetric. This is well known, it's classical. We, as I said, we work in the Hankel transform. And the issue for the challenge here for us to come to CEPID are of two kinds. First, to do all the analytical solutions we go analytically to the Hankel transform, but we have to come back to math. And this is a huge challenge for a complicated system. And the second one, the largest our systems are large. We have to do coupling of subsystems either iteratively or not. So this is the motivation that brought us to this center here.
If the material is not only transversely isotropic, but it's just general anisotropic, do you have some Green's function for it?
There are other Green's functions for Northwestern. There are some other, but we never implemented this. We used the basic model that was developed by one. But apparently we can include any other Green's functions into this scheme that we use. So typical solutions we have in the Hankel transform domains for displacements have exponential and some Bessel functions, and we have transformed them back. These constants are to be determined from boundary conditions as you specify. For example, the case of two half space divided in two media, we can put the load within the half space at this z prime depth. We divide in a layer median and a half space. This is quite classical actually. And we can we derive displacement and stress equations for the upper layer and with all the constants here, and we can go down to the half space, and which we already made use of Sommerfeld radiations condition to cut the constants where the exponents are positive. Here, this is classical way of incorporating Sommerfeld radiation condition. We can give boundary condition in terms of stresses, stress-free surface here. We also have continued displacement at the layer half space interface is also classical. We have a stress jump in the vertical direction, and then we can change it later on for other stress cases. So we are solving this classical problem here. Well, to obtain the stiffness matrix for the layer media is a classical standard procedure, having the equations for the layer, imposing continuity and equilibrium at the interfaces. So this is very classical, and they'll come up with a system, finite-like system with tractions and displacement, where you have the layers, and you may have a layer or a half space here. In case you have a half space here, this is the structure of the system. We have all the degrees of freedom at the layers interface here. So now, how we model the rigid circular plates. We divide the rigid circular plates into a system or a number of disks. We impose, they are massless, and we can do vertical and transverse and rocking loads on them. Typical solution of any equation of the problem is an integral equation of this kind, where you have the displacement anywhere at the continuum. We can also set it at the center of some places at the plate. We have tractions and the Green's functions here. The hard part to determine are exactly the Green's functions here, which are obtained numerically from the solution. But the main for the rigid plate is the classical. We divide into disks. You assume uniform state. You can assume actually any traction distribution. For displacement issues, not stress issues, the constant is a good one. We can discretize this equation, and then we have the hypothesis that radial tangential tractions are negligible in this case. So I have not happening as well. We can also include equilibrium and kinematic rigid conditions. We come to the definition of vertical compliance, in which W0 is vertical degree of freedom, and A is width of the radius of the disk, and these are elastic properties of the media and the excitation itself. So when we go to horizontal and rocking the horizontal degrees of freedom, the interesting issue is that you excite horizontally and there's a rocking here. So if, according to the properties of the media, there's a coupling or no coupling, we'll see that when it's a full space, properties are the same, there's no coupling. As the properties differ, coupling will increase. The horizontal load may be assumed as a sum of two simple functions. As we know, we can also model a concentrated moment around, like with a solution like this, with a linear distributed load about the y-axis here. So if we have the traction displacement, we can discretize, we can, this is the analog to what we already done in the vertical case. We can have a traction, or it's a classical discretized system with tractions in horizontal, tractions in the z direction, and you can find the solution to tractions here by imposing the displacement conditions there. It's not new. So we can pose horizontal and find this horizontal displacement, displacement can find forces, tractions in the z, and then x direction is all very classical. We have to add equilibrium in the horizontal direction, moment equilibrium as well. We can define to normalize the principal compliance. You excite in x, imagine x, you can excite in x and measure the rotation, or excite the force and measure the horizontal displacement. So this is the same actually for the only case. Now we come to the solution we are looking is there's a number of solutions we have. We look for a number of compliances, vertical, horizontal, and rocking, and the crossing coupling terms. So we take a look at some numerical results for the rigid plate. We can access the influence of inner and outer radius on the real and imaginary parts of the compliances. I won't go through to see what kinds of effects we can study, because most of them are already published. And so we can have it also the effect on the horizontal displacement. You see there's almost very little influence in a low frequency range according to the ratio of inner and outer radius. It's not the same for the imaginary part. That is related to the geometric damping of the system. But for the rocking moment, there is actually a stronger influence of the inner and outer radial geometry of the system. We can also do the study we study a material interface. There are several parameters here. The interesting issue might be you can vertical compliance and go from, actually as you change these properties, you may go to homogeneous half space to a full space. It's numerically consistent. This is the solutions we have. This is direct rocking compliance. You apply a moment and measure rotation degree of freedom. And also according to the properties, it may change the properties of the two media, interfacing media. It's not as interesting, it's not very important, again, for the horizontal solution. The effect of the media different on distinct materials is almost negligible. We can still have now study the effect of layering and properties of the layers. You can go on studying this for a long time. So we have three cases here, just for you to know. We have homogeneous, we have a load plate, rigid plate buried in a half space, and we changed the first layer, and then we kept the properties, but we did, sorry. So there's a number of studies regarding geometry and the embedment and property of the layer. You can access that in terms, again, of the vertical compliance, real and imaginary parts. We can go now to something for the cross compliances. It took us a while to do this, but we can have we are studying the cross compliances in the case that we have a full space, changing relation between the two media and coming to isotropic half space. And I think the cases are consistent. We can come from, go back. Case A is a homogeneous full space. Case F is a half space, loaded on a single half space. And we have actually, as we change and we modify the properties of the first media on the top, we can go from the full space to the half, from the half space, from the full space, from the full space to the half space, and we can see what happens to these coupling elements. The same with the rocking compliances is also there. This is now we can try to go from the cross compliances now. If we have a homogeneous full space, you know there's no coupling, and as you try to change the properties, the coupling of the horizontal rocking degree increases up to the case where you have the full space, which is the strongest possible coupling in this system. We have a lot of studies about changing the properties and making all compliances going from the case of full space to the half space. So different things. Now, how do we come to the next point? How we incorporated the elastic plate is the equation, the Riemann equation of elastic thin plate with this classical rigidity. The solution here is the classical, what Professor Rapace also did. We expand a solution in terms of polynomial with the generalized coefficients of n. So we're trying to express moments and shear forces and all the quantities as functions of these generalized coordinates. We can incorporate, we have here homogeneous boundary conditions, but we can introduce any other, but we did homogeneous boundary conditions in terms of moments and shear forces at the edges of the plate. We can write the boundary conditions also as function of the generalized coordinates. We can write strained energy of the plate also as functions of the generalized coordinates. We can write the kinetic energy of the plate as well as function as generalized coordinates. We can also include the potential energy of the soil due to contact attractions in this form. Can also be, this is where we're going to use the Green's functions. We can always also express the potential energy due to contact attractions as function of generalized coordinates. We can include the energy, potential energy of the external loads as well as this function of generalized coordinates. We can build a Lagrangian including potential and kinetic energy of the plates, the half space, and external forces. This is the form of the Lagrangian. We can include boundary conditions to Lagrangian multipliers here. We can minimize it. We can come to a system of equations in which you give forces and boundary conditions. You look up for generalized coordinates and Lagrangian multipliers being the elements of the matrix in here. So this is relatively easy to say, hard to implement, but we have experience. So validation of the procedure. We did a flexible plate within a half space. There's a solution from Pak and Gober from 92. And what we come is the verticals. We have all the vertical displacements here at the center, and real imaginary parts against the frequency. So our results agree we have a very good agreement with Ron Pak. So we also can determine the displacement along the radius for various degrees of embedment. So embedment of flexible plate is there. We can be able to change a relative stiffness between the plate and the soil to be considered in this case. We only give a constant value here. We can also analyze the inertial response. This is a central deflection under uniform distributed layers for different mass densities. From what we have here, mass of the plate, at least in this range here, up to 1.5, is not very significant. But other than that, as we increase the embedment ratio, the solution will change very much, coming from the surface of a half space. Actually, this is this half space, and this is a full space. Actually, as we increase the degree of embedment, you'll end up with close to the full space solution with oscillating terms around it. We checked it very carefully. This is really what happens in this case. So we also can have central displacement as for distinct frequencies. As embedment rate, you will see that you have symptotic behavior right here. So this is what we have been doing so far. We are working now on piles and piles groups. Is ongoing work. We have to do later on pile plate coupling, which is something Labaki will probably be doing. There is the issue of making a 3D solution because there are many issues you cannot deal with in the axisymmetric solution. We did a lot of work on implementing the evaluation of Green's functions on parallel, especially on GPU, and we had very successful results here. If the system is very large, one of the things we think we should do is build substructures and do interactive coupling between the groups and work on that. And we had the chance to do experimental validation here. We have a groups of pile foundations, and later on we have access to the whole series foundation. And the idea, as I mentioned, is to be able to understand the dynamics of what's being built there if we ever need to. Because I think traffic conditions are going to become coarse and around the synchrotron and things like that. So understanding the behavior of that system, the behavior of that system is worth doing, we believe. So this is one of the things we've been doing in the last year. Thank you very much.
We have time for questions. I have one question regarding modeling. For this fifth plate, you mentioned you plate is massless.
Yes.
Yeah. This will have an influence on the reaction of the
There are two ways to incorporate that. One is very simple. You just add mass to degree of freedom. Once it's rigid and you're doing it vertically, then you don't account the effect for the embedment ratio or the fact that you have built-in structure. But you can have an assessment of the influence of mass if you only do another equation. Other issues much more complicated. If you have a massive structure, you want to embed it again. That's also possible. We've done this. Rigid plate as well, regardless or on the surface or embedded or the system. Can be done.
So when you you have a code defines the displacement must be smaller and that number is a real number, right?
Yes.
So when you do your analysis here, you give me a frequency domain. So when you try to match the code, do you have to actually do a transfer from frequency domain solution to time domain solution?
Actually, this is the idea of dividing in the real and imaginary part is only because the displacement happens at different times. Displacement happens at different times with a phase.
Yeah.
So you have only to actually you can have the real displacement from that information of real and imaginary part. It's possible to have.
Just square and then
Yes,
add it up.
that's it. That's it. That's it. It's only a phase information there.
So that will be the biggest.
Yes. 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 At that given frequency.
Questions? I have one question. Right. I'm trying to recapitulate if I try to see if I understood. What happens this is supported by file files. And you're going to analyze essentially the evaluation of under different dumping conditions, external dumping, which is the embedding. The embedding means the soil. You have different. So
I'll rephrase it, but you understand the question, so go on.
No, if I am capturing correctly, or if I'm missing entirely the point. So is it, so different embeddings means some reflect different dumpings
So
on the plate, like dissipative.
There are two dissipative mechanisms in a system like this, provided that you assume bonded contact and you forget about friction and things.
Yes.
Okay. One is internal material damping from the soil,
From the soil, yes.
which is a viscoelastic solution. The same thing can be said about the plate. So you have internal. The other thing is energy carried away in form of waves that are not reflected back to the system, which is called a geometric damping.
I see. Yes, okay.
So this is a very interesting point, because when they had to decide, they're building now, with piles. But they never did detailed modeling. They built a raft foundation without piles and a raft foundation with piles. It's Disneyland to go there and measure, actually, because it's all there. And so there's a very interesting issue, as we all imagine it will be. If you have the foundation without the piles, it's less coupled to the soil than the one with the piles. So if you have an external excitation, you have smaller amplitudes at the foundation without the piles.
Smaller?
Smaller.
For any frequency?
For any frequency. And
So
then there's a dynamic response there.
I was worried about the road.
I was mentioning, I know the results for the transient case. So we have, for all the frequencies will not be the case. But when you excite outside, you have incoming field, and you have piles, the whole system is strongly coupled to the source, to the amplitude is large. Now, if you excite the foundation, it's the opposite. The system coupled with the piles will damp more rapidly than the one that has not coupled. So there's a trade-off. Depends on where your excitation is coming. If your excitation coming from outside, you wish to have, you don't wish the piles. If your excitation is coming from inside, you wish to have the piles. Which excitation is going to be critical here? They will have compressors. Today, if you walk the synchronous there, the guy on the line will notice. So you walk, and the guy on the line will notice, on the existing one. This is much...
Like a wooden floor or something like that?
It's a concrete slab floor.
Yeah, I know
you walk,
what I mean.
yeah, you walk.
If someone walks on the
beam,
oh.
so it's very sensitive. No one can actually know what because there will be compressors and other facilities around on top of the foundation on the raft. And other side will traffic outside.
Is it possible to measure the noise, both amplitude-wise and frequency range of the noise from the roads, right?
Yes.
Because you have
This is
the,
them. This is them.
they have done
Yes.
Dom Pedro, and then the other one very
Yeah,
easy.
the one from not from Dom Pedro, but from the road that you
Oh,
see.
from the road.
We have they have a lot of measurements on that. So, and they also have termed soil properties as well, but they don't have a model to do this very complicated calculation. We're also going to have a very simple model. This is a lot of work, but this is a relatively simple model compared to reality. So.
Yes.
We'll see. But if we know how it responds, we may be able to discuss putting a trench or somewhere, adding mass or whatever engineering issues we may have to make later on. So we have a basic understanding of how this works.
All right. We don't have any further questions. Thanks, Euclides, again.
Thank you.